In these notes, we're going to talk about something called a dipole moment. And a dipole moment is not a moment in time. A dipole moment is actually a force vector that describes an uneven distribution of charge, or a case where positive charge and negative charge are not in the same, the center of positive charge and the center of negative charge are not in the same place. And we're going to start with this example of hydrofluoric acid, this HF bond again, because it's a simple Lewis diagram to draw. And we've discussed the fact that the electron cloud is unevenly distributed. So that shape represents the electron cloud. Well, I'm going to superimpose a symbol for a dipole moment on top of this diagram, and it's going to be an arrow that's pointing towards the negative side of the molecule. And we put just a cross on the back side of the arrow because that's where the positive side of the dipole moment is represented. So just to make a note that this symbol represents a dipole moment. And a dipole moment is essentially a lopsided or uneven distribution of charge. So the electron density is concentrated on the right-hand side of the molecule. There's another way that dipole moments are diagrammed that I want to show you. So I'm going to draw our hydrofluoric acid molecule one more time. And it couldn't hurt to draw its electron cloud again. But I'm going to now add a symbol over here, which is the lowercase Greek letter delta. It's kind of a funny symbol to draw with a minus sign, and the lowercase Greek letter delta over here with a plus sign, and tell you what those means. The delta plus and delta minus show partial charges. And what we mean by partial charges is this doesn't have a +1 charge the way a sodium cation would have a +1 charge. It's really just a partial charge. But this is important because there's more electron density over here. There's a slightly negative charge over here. So there's a slight concentration of electrons, and that is going to sometimes produce electrostatic forces of attraction or repulsion to other molecules. And that's what's consequential about polarity. So let's now look at an example of some molecules, because it turns out a dipole moment can exist in a bond, or it can exist in a molecule. And just because a molecule has a bond dipole moment doesn't mean it has a molecular dipole moment. So let's go through two examples. The first example we'll go through is water, which is, of course, a common example for lots of reasons. And I'm going to draw a water molecule like this. So it's oriented sideways. We know the basis for this molecular geometry now, and the basis for that being the correct Lewis diagram. And I'm now going to draw with a couple of different colored pens just to make it a little clearer, although it may not be necessary for you to do that. I'm going to draw a bond dipole here and a bond dipole here. And it should make sense that my bond dipoles are pointing towards oxygen, because oxygen is more electronegative, and it's also where the electron density is. And so, just to be clear, those are bond dipoles. But I'm also going to, with a red pen, or maybe if you just are using one color of pen, make a large dark line here that represents the molecular dipole. And it may make intuitive sense that those two green bond dipoles are going to add up together to give you this bond dipole, this molecular dipole right here. So this is the overall dipole moment that results. Now, here, the two bond dipoles have resulted in there being a net or overall molecular dipole moment, but that isn't always the case. We'll show another example where even though the molecule has bond dipole moments, there is no net molecular dipole. And that exists in CO2. We've drawn the Lewis diagram for CO2 before, and this is what we end up with. A linear molecule with a 180-degree bond angle. And that's important because even though there are bond dipoles that would be oriented like this, and sometimes it's helpful to draw them right on top of the molecule, but here I've just put them above or to the side just to make it more clear. The bond dipoles are pulling in opposite directions, and because this is a 180-degree bond angle, in other words, because that's a linear molecule, there is no molecular dipole. And that's because those two bond dipoles cancel each other out. If you have one force vector that's pulling to the left at the same magnitude that another one is pulling to the right, then they're going to cancel each other out and there's going to be no overall dipole moment. So some molecules are polar because they have a molecular dipole, and some molecules are nonpolar because they have no molecular dipole. And nonpolar molecules may have bond dipoles, or they may just have no polar bonds and be nonpolar for that reason.